Welcome to this problem walkthrough. Today, we will be solving LeetCode problem number 1507, titled Reformat Date. We'll explore the problem requirements, analyze different solution approaches, and discuss their complexities. Let's dive in. In this problem, you're given a date string in the format day, month, year. The day includes a numerical value followed by a suffix, such as first, second, or 21st. The month is a three-letter abbreviation like Jan for January or October for October. Lastly, the year is a four-digit number, such as 1990 or 2023. Your task is to transform this input into the ISO date format, which is YYYIMMDD. This involves converting the day to a two-digit number without its suffix, mapping the month abbreviation to its numerical representation, and ensuring all components are properly formatted with leading zeros where necessary. Let's look at some examples to better understand how this transformation works. In the first example, the input date is October 20th, 2052. Here, we can break down the components as follows. The day is 20th, which becomes 20 after removing the suffix. The month is October, which corresponds to 10. Finally, the year is 2052. When we combine these components in the YYYIMMDD format, the output becomes October 20th, 2052. Notice how the day and month are zero padded to ensure two digits each. In the second example, the input is June 6, 1933. The day is 6th, which simplifies to 06. The month is June, corresponding to 06, and the year remains 1933. The reformatted date is therefore June 6, 1933. Now, let's look at the third example with the input string March 11, 2000. Breaking it down, the day is 11th, which simplifies to 11 after removing the suffix. The month is Mar, which corresponds to the numerical value 03. The year remains as 2000. Combining these parts in the required YYYIMMDD format gives us the output March 11, 2000. This approach follows the same pattern as the previous examples, ensuring the day and month are always represented as two-digit numbers, even if the original input is a single digit. There are a few constraints and rules to keep in mind as you solve this problem. First, the input string is guaranteed to be valid and always follows the day-month-year format. The day will always be a valid value between 1st and 31st, while the month will be one of the 12 standard three-letter abbreviations, such as Jan, February, or Dec. The year will always be a four-digit integer within the range of 1900 to 2100. Additionally, there are no extra spaces before or after the input string. The output date must strictly follow the YYYIMMDD format, ensuring zero padding for single-digit days and months as required. When handling edge cases, it's important to consider scenarios such as single-digit days. For example, July 5, 2005 must be reformatted to July 5, 2005 with a zero-padded day. Similarly, months with varying numbers of days, whether 30 or 31, must be processed accurately based on the given input. Be cautious not to introduce any leading zeros into the year or month values unintentionally. Finally, ensure the implementation handles the upper bound of the year range correctly, such as December 31, 2100, which should result in the output December 31, 2100. By addressing these details, you can ensure your solution is robust and handles all valid inputs effectively. To tackle the problem of reformatting a date string, we first considered the brute force approach. Here, the intuition is to directly parse the given string by extracting its components, the day, month, and year, through string splitting and manual transformation. For example, the day component includes a suffix like c, nd, or th, which we can strip out to get just the numeric value. Similarly, the month abbreviation, such as Jan or February, can be converted into its numeric equivalent using a predefined dictionary. Once these components are processed, they can be concatenated into the desired format, YYYIMMDD, using basic string formatting. This approach is efficient in terms of time and space complexity because the input size is fixed, a single date string. However, it does involve manually handling suffix removal and formatting, which, while simple, might not scale well for variations in date formats. We then explored an optimized approach using regular expressions. The idea here is to define a regex pattern that can directly match and extract the day, month, and year components from the input string. This eliminates the need for manual string manipulation, making the implementation more concise. After extracting the components, the month can still be converted to its numeric value using the same dictionary as before, and the final date can be assembled in the YYYIMMDD format. While this approach retains the same time and space complexity as the brute force method, it introduces trade-offs. On one hand, it's more compact and elegant for someone familiar with regex. On the other hand, regex can be less readable and harder to maintain, especially for developers who are not well-versed in it. So, while efficient, this method might not always be the best choice when simplicity and long-term maintainability are key considerations. Given these considerations, we ultimately decided on a hybrid approach that combines the simplicity of manual string parsing with the efficiency of dictionary lookups for months. This approach avoids the complexity of regex while keeping the implementation clear and straightforward. The process involves splitting the date string into its components, removing the suffix from the day using slicing, and mapping the month abbreviation to its numeric equivalent with a dictionary. Finally, the components are formatted into the desired YYYIMMDD structure. This strategy strikes a balance between simplicity and efficiency, avoiding unnecessary overhead while remaining easy to debug and maintain. It's particularly suitable for this problem, where the input format is guaranteed to be consistent, allowing us to focus on clarity and robustness without sacrificing performance. While this hybrid approach is slightly less concise than the regex method, it excels in readability and maintainability. By focusing on clarity, we ensure that the solution is robust and easy to understand. A few key observations make this method especially effective. First, the day suffix, such as SC or ND, can be consistently removed using slicing, simplifying the processing of the day component. Second, since month abbreviations are fixed, they can be efficiently mapped using a dictionary, avoiding any need for complex logic. Finally, Python string formatting capabilities allow us to seamlessly assemble the date into the desired YYYIMMDD format. These insights, or aha moments, highlight how a thoughtful approach can simplify the problem while balancing performance and maintainability. Let's begin by understanding the problem. We are tasked with converting a date in the format day-month-year, such as February 21, 2023, into the standard numerical format YYYIMMDD, which would be February 21, 2023. The challenge lies in handling the ordinal suffixes like SC, ND, RD, or TH in the day component and mapping month names, which may be abbreviated like February or written fully like February, to their respective numeric values. To solve this, we break the problem into clear steps. First, we parse the input string by splitting it into three components: day, month, and year. For example, given the input February 21, 2023, splitting by spaces results in an array, 21st February 2023. Next, we clean the day component by removing the ordinal suffix. This can be done using slicing or regular expressions to strip the last two characters if they are non-numeric. For instance, 21st becomes 21, which is now a numeric string ready for further processing. Now that the day component is cleaned, we move to the month. The goal here is to convert the month name, such as February, into its corresponding numeric value, in this case, 02. To achieve this, we use a dictionary that maps both full and abbreviated month names to their respective numbers. For example, Jan maps to 01, February to 02, and so on, up to December, which maps to 12. By simply looking up the month in this dictionary, we can retrieve its numeric value efficiently. For the year component, no additional processing is usually needed, as it's already in the correct 4-digit format. Finally, we combine the clean day, numeric month, and year components into the desired YYYIMMDD format. This can be done using string formatting or concatenation. For example, combining 2023, 02, and 21 results in the final output February 21, 2023. There are a few important insights to consider when implementing this algorithm. First, handling ordinal suffixes like SC, ND, RD, or TH is crucial to ensure the day component is purely numeric. Stripping these suffixes guarantees uniform formatting. Second, using a dictionary to map month names to numeric values is not only efficient but also makes the code more readable, as it can handle both full and abbreviated names seamlessly. Third, we need to account for edge cases. For instance, single-digit days like January 1st, 2023 should be 0 padded to 01. Similarly, invalid inputs, such as 32nd February 2023, should be handled gracefully, either by raising an error or returning a default value based on the requirements. Lastly, ensuring output consistency by 0 padding all components, such as 02 foot for February, is essential to maintain the YYYAMMDD format. To implement this algorithm, we rely on two main tools: dictionaries and string manipulation. The dictionary is used for mapping month names to their corresponding numeric values. For example, a dictionary like Jan. 01, February, 02, Dec. 12 allows quick lookups for both full and abbreviated month names. String manipulation is used to clean and format the day and year components. Techniques such as slicing or regular expressions help in removing ordinal suffixes from day values, while straightforward concatenation or formatting methods are used to assemble the final date string. When analyzing the complexity of this solution, the time complexity is O(1), as all operations, including splitting strings, dictionary lookups, and simple manipulations, are constant time due to the fixed size of the input. Space complexity is also O(1), because we only use basic variables and a dictionary of fixed size containing 12 months. Let's walk through an example to solidify the process. Suppose the input is February 21st, 2023. First, we parse the input string into its components, 21st, February, 2023. Next, we clean the day component by stripping the ordinal suffix, resulting in 21 foot. Then, we convert the month by looking up February in our dictionary, which gives 02. The year, 2023, requires no changes as it's already in the correct format. Finally, we combine these components, 2023, 02, and 21, into the desired format YYYAMMDD. The output is February 21st, 2023, which is the correctly formatted date string. This Python implementation solves the LeetCode problem number 1507, Reformat Date, where the task is to convert a date string from the format day month year into YYYAMMDD. The function ReformatDate uses a dictionary to map the textual month names to their respective numeric values, ensuring a straightforward lookup. The input string is split into three components: day, month, and year. The day component is cleaned by removing the ordinal suffix, e.g., sig, nd, rd, th, using slicing, day, :2. If the day is a single digit, it is padded with a leading 0 to maintain the two-digit format. Finally, the function constructs and returns the date in the YYYAMMDD format using an f string, pulling the year directly, the month from the dictionary, and the day after processing. This approach ensures the output is correctly formatted and handles all cases specified in the problem. The solution is efficient with O(1) time complexity since the operations involve fixed string manipulations and dictionary lookups. Here, we start by creating a map to associate each month abbreviation with its corresponding numeric value. This will help us later when converting the month part of the date string. For example, Jan maps to 01, February to 02, and so on. After defining this map, we split the input date string using the split method, which breaks the string into three parts: the day, month, and year. These parts are stored in the parts array. Next, we extract each part by its index, assigning the first part to day, the second to month, and the third to year. Since the day part includes a suffix like sig, nd, rd, or th, we use the substring method to remove the last two characters, leaving only the numeric portion of the day. Now, we ensure that the day is always represented with two digits. If the day is a single digit, such as 1, we prepend a 0 to make it 01. This ensures consistency in the output format. Finally, we construct the reformatted date string by concatenating the year, the numeric representation of the month retrieved from the months map, and the two-digit day, separated by hyphens. This matches the required YYYAMMDD format. The method then returns this reformatted date as the output. To reformat the given date, we start with the input string, which in this case is October 20th, 2052. First, we need to parse this string into its individual components: day, month, and year. Using Python's split function, we separate the string by spaces. This gives us three parts: day is 20th, month is October, and year is 2052. Once we have these parts, the next step is to process them individually. For the day, we need to remove the ordinal suffix, which in this case is th. By slicing the string to exclude the last two characters, we get 20. Since this is already in a 2-digit format, no further changes are necessary. Next, we need to handle the month. The month is provided as an abbreviation, October. To convert it into a numeric format, we use a dictionary that maps month abbreviations to their corresponding numeric values. In this dictionary, Jan maps to 01, February to 02, and so on, up to Dec, which maps to 12. By looking up October in the dictionary, we find that it corresponds to 10. With the month converted, the final step is to combine the processed components. Using Python's f-string formatting, we arrange the year, month, and day in the desired format, YYYAMMDD. This results in the output October 20th, 2052. Now, let's look at another example to solidify this process. For the second example, the input string is June 6, 1933. Just like before, we start by splitting the string into its components, day, month, and year. This gives us day as 6th, month as June, and year as 1933. The next step is to process the day. Here, we again remove the ordinal suffix, which is th, by slicing off the last two characters. This leaves us with 6. However, since the day must always be in a 2-digit format, we check its length. If the length is only 1, we prepend as 0 to make it 2 digits. After this adjustment, the day becomes 06 foot. With the day properly formatted, we move on to the month. The month is given as June, which we convert using the same dictionary that maps month abbreviations to numeric values. Looking up June in the dictionary, we find that it corresponds to 06. With both the day and month processed, we can now combine all three components into the desired format. Using the f-string, we place the year, month, and day in the YYYAMMDD format. The result for this example is June 6, 1933. Now, let's consider a third example to reinforce these steps. In the final example, the input string is September 1, 2020. We begin by splitting the string into its components, day, month, and year. This gives us day as 1st, month as Sep, and year as 2020. Processing the day involves removing the ordinal suffix, which is a se, by slicing off the last two characters. This leaves us with 1. Since the day must be 2 digits, we check its length and prepend as 0 if necessary. Here, the day becomes 01 foot. After processing the day, the next step is to handle the month. The month, Sep, is converted using the same dictionary as before. Looking up Sep, we find that it corresponds to 09. Finally, we combine the year, month, and day into the YYYAMMDD format using an f-string. The result for this example is September 1, 2020. This completes the reformatting process for the given input. Each step ensures that the input string is parsed, processed, and formatted correctly to produce the desired output. The time complexity of the solution can be analyzed by breaking down each step involved in processing the input date string. First, the months dictionary is a fixed structure containing 12 key-value pairs for mapping month names to their numerical equivalents. Accessing any value in this dictionary is an O(1) operation, as dictionary lookups are constant time on average. Since the dictionary is predefined and not created dynamically during execution, it contributes O(1) to the overall complexity. Next, the date.split operation is used to separate the input string into three parts, day, month, and year. This split operation has a worst-case time complexity of O(m), where m represents the length of the input string. Then, we process the day string. Extracting just the numeric portion of the day using slicing is an O(k) operation, where k is the length of the slice being extracted. However, since the day string is always a maximum of 4 characters, this operation can be considered O(1). Additionally, padding the day with a leading 0 when necessary involves a simple length check and string concatenation, both of which are constant time operations. Therefore, the day string processing step collectively takes O(1) time. Now, let's analyze the time complexity of the remaining steps. For the month, we perform a lookup in the months dictionary to retrieve the corresponding numerical value. As mentioned earlier, dictionary lookups are O(1) operations on average, so this step is extremely efficient. Then, we construct the final output string in the format YYYIMMDD using an F string. This operation involves concatenating the year, month, and day strings, which have fixed lengths. Since the resulting string always has a length of 10 characters, the time required for this concatenation is O(1). When we sum up all these steps, the dominant factor remains the split operation, which is O(m), while all other steps contribute O(1). Therefore, the overall time complexity of the solution is O(m), where m is the length of the input string. Next, we consider the space complexity of the solution. The months dictionary is a fixed data structure containing 12 entries, which does not grow with the size of the input. As a result, it requires constant space, O(1). The split operation generates a temporary list containing 3 substrings, day, month, and year. The space required for this operation is proportional to the length of the input string, making it O(m). Additionally, intermediate variables like day, month, and year store references to these substrings or new fixed-length strings. Since these variables store a small, constant amount of data, they use O(1) space. Lastly, the output string has a fixed length of 10 characters, so it also requires O(1) space. In summary, the dominant part of the space complexity comes from the temporary list created by split, which gives the solution an overall space complexity of O(m). Summarizing the space complexity, the temporary list created during the split operation is the primary contributor, scaling proportionally with the input length, O(m). All other operations, such as dictionary storage, intermediate variables, and the output string, require constant space, O(1). When compared to a brute force or naive approach, which might involve manually parsing the string or using multiple regular expressions, the current solution is significantly more efficient. A naive approach could increase the time complexity to O(m squared, as repeated substring operations or regex evaluations would add unnecessary overhead. Similarly, space usage could grow due to storing intermediate results. In contrast, the current approach leverages built-in string operations and a dictionary for constant time lookups, achieving O(m) time and O(m) space. This makes the solution both optimal and practical for the problem. Finally, let's analyze the best, average, and worst-case scenarios for this algorithm. Regardless of the specific content of the input string, the algorithm processes it deterministically in the same manner. This means that the time complexity remains O(m) in all cases, where m is the length of the input string, as the operations involve splitting the string and performing a constant number of lookups, checks, and concatenations. Similarly, the space complexity is also O(m), dominated by the temporary list created during the split operation. Since there are no variations in processing based on input characteristics, the best, average, and worst-case complexities are identical, O(m) for time and O(m) for space. This consistency makes the algorithm predictable and efficient under all conditions. When solving problems like reformatting dates, there are several common mistakes to watch out for. One frequent issue is ignoring edge cases, such as invalid inputs like empty strings, null values, or dates with incorrect formats like 32/13/2023. These types of inputs can cause runtime errors if not handled properly. This often happens because edge cases are overlooked during testing. To address this, it's essential to write test cases that cover invalid inputs and boundary conditions. Another mistake is incorrectly splitting strings. For instance, assuming that the input format is always dd/mm/yyyy without considering alternatives like mmddyyyy or yyy.mm.dd. This can lead to parsing errors if the input doesn't match your assumption. The root cause here is not accounting for the constraints or variations in input formats. Using regular expressions or a robust parser can help handle multiple formats reliably. Lastly, hard-coding values, such as assuming the day is always at index 0, can make your solution break when the format changes. This often occurs when rushing to implement a solution without considering flexibility. Instead, dynamic parsing based on format descriptors makes your code more adaptable to changes. Another pitfall to avoid is ignoring time complexity. Overly complex solutions, such as using multiple nested loops or redundant string processing, can lead to inefficiency. This often arises from a lack of awareness about simpler, optimized methods. To prevent this, analyze the problem carefully and aim for solutions with time complexities like O(n) or O(1) whenever possible. Additionally, leap year validation is a common oversight in date-related problems. For example, failing to account for February 29th in leap years can produce incorrect results. This happens when calendar-specific rules are overlooked. To handle this, ensure you incorporate leap year checks, such as verifying that years divisible by 4 are leap years, except those divisible by 100 unless they are also divisible by 400. Addressing these issues not only improves your solution's accuracy but also makes it more robust and efficient. When tackling date-related problems during interviews, certain strategies can give you an edge. First, recognize recurring patterns. Many date problems involve string manipulation, parsing, and validation. Identifying these patterns early can help you decide whether to use tools like regular expressions or built-in libraries. It's also crucial to ask clarifying questions. Confirm the expected input format and constraints with the interviewer. For example, ask whether multiple date formats are allowed or if invalid dates should throw an error or be ignored. Be aware of trade-offs as well. For instance, manual parsing offers more control but is prone to errors, whereas using libraries simplifies the process but may lack flexibility. Writing modular code is another valuable practice. Breaking down your solution into smaller functions, such as validate_date, parse_date, and format_date, makes debugging and testing much easier. Finally, adopt a robust testing strategy. Ensure your test cases cover normal scenarios, edge cases like 31/02/2023, and corner cases such as very large or very small years. To deepen your understanding, you can explore related problems that emphasize similar skills. For example, LeetCode 1154, Day of the Year, involves converting a date string into the day of the year and focuses on date parsing and leap year logic. Another problem, LeetCode 1360, Number of days between two dates, requires calculating the difference in days between two valid dates, emphasizing date manipulation and validation. Of course, the problem we're discussing, LeetCode 1507, Reformat Date, challenges you to reformat a date string from one format to another, requiring parsing and formatting skills. Lastly, LeetCode 1185, Day of the Week, asks you to determine the day of the week for a given date, combining parsing with modular arithmetic. For alternative approaches, you can leverage built-in libraries like Python's datetime or Java's simple day format. These libraries handle edge cases, such as leap years and multiple formats, automatically. However, if the problem explicitly prohibits library use, you'll need to rely on manual methods. If you can't use built-in libraries, manual parsing is a viable alternative. With this approach, you split the string and manually validate and reformat its components. This method gives you full control over the process, making it suitable for restricted environments. However, it can be error-prone and time-consuming if not implemented carefully. Another effective tool is regular expressions. By using regex patterns, you can extract and validate the components of a date efficiently. This approach is compact and handles multiple formats effectively, but it comes with its own challenges. Complex regex patterns can be difficult to debug and maintain, so they should be used judiciously. Balancing these approaches based on the problem's constraints and your comfort level will help you craft a robust solution tailored to the given requirements. Great job completing this problem. In this session, we tackled the reformat date problem, focusing on efficient string manipulation techniques. Remember to keep practicing similar problems to strengthen your skills. Thank you for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!